All right, we're starting chapter 17, which is all about the graphs of sine, cosine, and tangent. So taking our trig functions and taking a look at what their pictures look like when we graph them. So kind of like when we do linear equations, we talk about solving and we do all sorts of things with them, but we also look at their picture or their graph. So that's what we're going to be digging into here in chapter 17. Today we're going to look at sine and cosine, and they're really kind of a neat, different type of graph than maybe you've seen before because they're called periodic functions. They're an example of a graph that cycles through the same set of values over and over again and just repeat sort of the same pattern, which actually happens a lot in real life situations. So the example I have up on the screen right now is the Ferris wheel. As the Ferris wheel goes around, maybe you've ridden on one of those. Kind of scary for me sometimes. They get kind of high, but anyway, time and height. So if you think about the time that you're on the Ferris wheel, your height cycles with respect to time. So when you start off at your initial beginning ride, so when you get on the Ferris wheel, as time goes by, you go up to the top of the Ferris wheel, the highest height, and then you go back down to the bottom where you started, and you go back up and back down, and that keeps cycling over and over again. Classic example of a sine or cosine graph. So they're called periodic or cyclic functions because they cycle through the same set of values. So that's a great real life example to take a peek at. So periodic functions repeat these regular intervals called cycles. So it cycles through a set of values. So the length of the cycle, how long it takes to get through a complete cycle, is called its period. So if you think of the Ferris wheel, that would be the time it takes to go all the way around the circle. Like how long is that? So say it takes 5 minutes. That would be the period or the length of the cycle. That's a big part of the calculations that we're going to be making. How long does it take for sine and cosine to cycle through one set of values? So we're going to look at that today. Another idea that we talk about when we look at periodic functions is not only how long it takes to cycle, but also how high the graph goes and how low the graph goes. So that's something called amplitude. So in physics, I know you talk about waves and things like that, and amplitude definitely comes up there because the waves, like sound and light waves that you think of in physics, is these kinds of graphs, exactly that. So when you're looking at the highs and the lows, that's talking about the amplitude. So the amplitude for sine and cosine is half the difference between the maximum value, so wherever the top of the graph is, and the minimum value of the function. So basically the difference between minimum, if I can spell correctly here, that looks terrible. When we look at figuring out what that value is, it's really kind of the distance from the middle to the top then, or the middle to the bottom. So I'll kind of draw it on this picture here so you have an example of what that looks like. So the amplitude would be taking the distance from the maximum value up here to the minimum value down there and taking half of it. So it's half of that distance. So basically kind of the middle to the top or the middle to the bottom. So guesstimating on this graph, it looks like it's about, I don't know, 70-ish up here, and it looks like it's about 10. So the total height of the wave from bottom to top, that would be 70 minus 10, so that would be a height of 60. So then the amplitude, I'll just use A for amplitude, would be half of that, which would be 30. So really how we kind of think of it is it's the distance from the middle to the top, so this would be the amplitude up here, or the middle to the bottom. So that distance of 30. So amplitude is a big part. It's something how we measure the height of a wave. So if you think about even like a wave in the water, when we talk about the amplitude of it, we're talking about the height. So from the middle to the top, middle to the bottom, or half of the distance between the max and the min value. So if you want to think of it sort of as a, I guess, as a formula, it would be 1/2 the max value of the wave minus the minimum. So amplitude and period are really the two big things that we talk about when we just express what a wave looks like sine or cosine. So, and the amplitude, just to make sure we're clear on this, is always expressed as a positive value because it's a distance, kind of like absolute value, like the distance from 0. Think of 0 like the middle of the graph. So amplitude is always a positive value because we're looking at how far away it is from the middle. So makes kind of a nice idea to be able to deal with that. The other thing I want to draw on this picture just to make sure that we have it. So I talked about amplitude. Let's talk about what the length of a cycle would be. So I'm just going to grab, so we can talk about the period. I'm going to grab a highlighter here. So when I look at the period value for this one, it's really taking a look at a complete cycle. So being able to tell what's happening and where that's going to be. So for this one, we start at a location, we go up to the top, and when we get back to that same location again, that would be the the length of a period. So I just highlighted one, and then we'd have another one. It repeats again. So let me grab a different color here. So here's the second one. So this one actually shows 2 complete cycles. So we can take a look and see what that would be. How long did it take to get through 1 complete cycle? Well, it looks like it was 3 minutes. So the period of this function would be 3 minutes. That's how long it took this Ferris wheel to go all the way around. So 3 minutes, and then again there's another 3 minutes. So the length of a cycle is always going to be the same in a periodic function. It takes the same amount of time every time you go around. And then the amplitude of the height there was the 30 feet. All right, so let's take a look at what this means for us when we talk about actual values that we're going to be dealing with. So when we look at sine or cosine, then actually calculating, I know we talked about the idea, what those are. It's half the difference between the max and the min. So I know we already kind of said that. We don't necessarily need to kind of write that again, I guess. Half the difference between the maximum value and the minimum values of the function then. So if we're thinking of it and kind of in terms of this mathematical thing now, not just like as a Ferris wheel height, the amplitude is always expressed as a positive again. Let's take a look at what it looks like for an actual sine or cosine kind of graph. What you're going to see is you're going to see angle measurements on the x-axis. So we're going to go ahead and do a little bit of labeling here. So there's going to be angle measurements on the x-axis. So in degrees it'd be things like 0, 90, 180, 270, 360, but in radians it'll be things like 0, pi over 2, pi, 2 pi, and so on. So we'll have angle measurements on the x-axis, and then our y-axis is going to be whatever SOHCAHTOA ratio that is. So our domain value is an angle measurement, so like what we're putting in for our x, and our range value is the ratio that we get for our answer. So for sine and cosine, those SOHCAHTOA values, those would be the outputs. All right, so let's talk about period and amplitude then for this. So let's just take a look at the example you're given. This is a periodic function, so it's one of the types that we're going to be talking about today. So the period is the length of 1 complete cycle. So we have to try to figure out where are we seeing this cycle. So what do we see as the pattern that's repeating? So I'm going to go ahead and grab my highlighter again. Sometimes it's easier to see. I'm just going to start at 0. It looks like it's at its maximum up here. We want to see when does it get back to its maximum. So that right there would be 1 complete cycle. That's the period of the function. So when I'm looking at my picture, that period, oh dear, the period, I was going to grab that and it didn't really work out. The period of the function would be that length right there, however you want to label that. So the period is this distance right here. So let's take a peek. Where is that labeled on the graph? Well, it looks like it starts at 0 and it goes to pi. So the length of the period of this function would be pi radians. That's how long it takes. That it has to go through that angle. Let's talk amplitude for a second. See if we remember about amplitude. Remember, amplitude is half the distance between the maximum and the minimum. So let's see if we can read what the max and the min values are. Looks like, what are we going up by? If this is 1, that's halfway to, we must be going by a half. So it looks like that's 1.5. So our maximum value is 1.5. What's the minimum down here? Well, that would be 0.5, -1, -1.5. So the minimum is at -1.5. So we want to figure out what is the distance between them. So the total height change between the max and the min, and then divide by 2. All right, well, what's the difference between the max and the min? To calculate our amplitude, it's going to be 1/2 of that 1.5 minus a -1.5. You can just look on the graph. It's even easier to tell there. We're 1.5 above and we're 1.5 below. So we're going to be doing half of 3 total distance, plus a positive, remember, so that's going to be 1.5. And hopefully that makes sense if you look at the picture. If this is the middle of the graph, we're going to talk a lot about this as we move forward. The amplitude then is going to be the distance from the middle to the top, so that would be 3, and the middle to the bottom would also be 3. So when we're looking at our picture, that's how we would calculate an amplitude. So if we're given a graph, we can always tell the period, the length of a cycle, and also the amplitude by just doing those quick calculations on our graph. So it's a good thing to be able to recognize what is periodic and what isn't. So be able to find those values. All right, so let's take a look. I'm going to give you some pictures. And what I'd like you to do is see if you can figure out, are these periodic or not? So these are kind of yes or no. Do you see a pattern that repeats? And if so, great, that would be periodic. If it's not a pattern that's repeating, then it's not. So I'm going to give you a second. Go ahead and pause the video. Circle what you think. Which ones are periodic? Which ones aren't? All right, well, let's start with this first one here, periodic. They even have them listed for you. So what's repeating is each of these little sections. So when you think about what they're looking at here, this one is a single period. Then we have another one. That's 2. There's 3. There's 4. Definitely repeating the same set of values. Which other one would be periodic? Well, it looks like the one right below. We have a cycle. Say we start here, goes up to the top, goes back down, and doesn't it start again with the same thing? Starts at the bottom, goes up top, and comes back down. We definitely have the idea of a cycle there. So that is definitely periodic as well. So it's just important to look for, is it the same set of values repeating over and over again, or is it completely random? All right, how about the one on the right on the top? That's sort of all over the place. It's not actually repeating the same set of values at all. It's pretty random, kind of like the stock market maybe. That's not going to be something that is periodic. We can't describe it as one of these functions. How about the next one? What do you think? Can we trace something that looks like it's repeating? You can pretty much start anywhere you want, but say we start at the bottom, go up, we go down a little, and then we get to the bottom again. It does not repeat. Up to the top, down to the little one, and back to the bottom. Definitely periodic. And we could calculate then what's the length of one complete cycle. What's the period? We could calculate the amplitude top to bottom, and we could figure out what's happening with each of those waves. So it's important to see if we can recognize, is something repeating the same thing over and over again, or is it not? All right, so let's take a look at the last two here. What do you think? Periodic or not periodic? Thoughts, ideas. Go ahead, pause the video, see what you think. All right, well, the problem with this one, it's not doing the same value over and over again. It is a pattern, but it's not repeating the same set of values. So this one would not be periodic because it's not going back and forth between the same things. It's just continuing to increase. It's doing something different each time. The second one's a little tricky to be able to tell, but I'm going to complete the rest of the picture. This one would go down, and then this one would come up. This is actually one of our parent graphs we're going to be doing later in the chapter. If I complete that picture, maybe it's a little bit more obvious, but this is definitely repeating, right? When we look at each of these, we have one here, we have another one that looks exactly the same, and another one that looks exactly the same. So that is definitely a periodic function. It's the same set of values repeating itself. So yes, this would be periodic, and we hopefully would be able to actually describe what's happening with that, with an amplitude, a period, and all of those things. So our goal ultimately is to be able to recognize which of these kinds of functions are periodic and what kinds of real life applications do we use for these, like the Ferris wheel height and things like that. All right, so we're going to be using sine and cosine today, like I said. So sine and cosine are two examples of periodic functions. So we're going to graph their parent graphs today. So not unlike when we first learn about parabolas, we see what the basic parabola looks like, that U-shaped graph or absolute value or a line. Today we're going to do sine and cosine. What do those basic graphs look like? So you're going to need your unit circle, so make sure you have your unit circle handy. We're going to be just pulling the numbers off of those, and remember, cosine is the x, so the first coordinate in our ordered pairs, and sine is the y. So we're not going to do every point, but we're going to do way more on this first graph just to make sure that we know what's happening. So we're going to start with sine, and we're going to fill in the table of values right from your unit circle. So I'm going to go ahead and have you have your unit circle handy, and we're going to complete the table. So I'm going to have you pause the video here in a second to do that, but I just need you to fill in. We're doing y equals sine of x. Might be a nice idea to kind of highlight that for yourself, but that means we're looking at the y values. So sine of 0, I'm going to kind of start in the middle. Sine of 0 here then would be 0. At pi over 4, sine would be root 2 over 2. Now, every root 2 over 2, that's kind of hard for people to think about when they graph. So I guess I would just think about what is that as a decimal, so we know what kind of number we're dealing with. So root 2 divided by 2, we'll call it about 0.7 when we fill it into our table, just to make sure we have a number to like approximate when we're trying to do the graph. All right, so the next one then is pi over 2, which they've already filled in for you, which is 1. That's the maximum value. 3 pi over 4. Again, we're looking for the sine values where there's another 0.7. Pi 0, back to 0. So notice we're cycling kind of through those values. 5 pi over 4. Oh, look, we went down, so negative 0.7. 3 pi over 2, we're down here at negative 1. That's in the table. 7 pi over 4, again, we're down there at negative 0.7. And then at 2 pi, we're all the way back around to 0. Now, if you keep going, if I went around the circle all the way once and then kept going, wouldn't I get to the same values then again as I went around the circle again? And that's the whole idea of a periodic function, that we keep cycling through the same set of numbers. All right, well, what about the negative angles? Remember, that just means you're going around in the opposite direction. So let's see what that would look like. So negative pi over 4 would mean this. So it's the same as 7 pi over 4. So it's still this value. We're just going in the opposite direction. Negative pi over 2, that's the same as 3 pi over 2. So negative 1. Negative 3 pi over 4 is the same as a positive 5 pi over 4. So negative 0.7. Negative pi, that's halfway around. So 0. Let's see, negative 5 pi over 4, all the way around to here. That's the same as positive 3 pi over 4. You should notice we keep cycling through the same values. Negative 3 pi over 2, like negative 270, that gives us our positive 1. Negative 7 pi over 4, same as pi over 4. That gives us our 0.7. Always these were 2 over 2s, but we're just putting in the decimal for graphing. And then all the way around, one complete revolution would be back to 0. Now, we could keep going again, right? We get to the same values over and over and over again. That's why these are called, again, periodic functions. They cycle right through the same set of values. All right, so we're going to plot some points. We're going to connect them up because I only picked a few of them, right? We could have done 30s and 60s. Gosh, we could have put in any values we wanted, right? But we're just picking ones that were easy that we know from our SOHCAHTOA ratios. Let's pick a little, I guess I had the angles in there for you already, but let's pick a scale here. I think just to not make it super tiny, I'm going to do 2 boxes for 1 just to make this a little bit easier to read. Okay, so let's go ahead and plot our points. So 0, 0. Pi over 4. Okay, let's make sure we understand what's labeled. This is pi over 2. So that means halfway would be, that's like 90 degrees, right? So halfway would be 45 or the pi over 4, so just so you know where to put your dots. So at pi over 4.7-ish, that'd be about there. Pi over 2, it's 1. Go ahead and just plot your points. So if you want to take a moment and pause the video, you can go ahead and do that, or you can kind of plot with me. 3 pi over 4 would be halfway there. Pi is 0. Negative 0.7, negative 1. Negative 0.7, 2 pi. Now, it would technically continue there, so we could keep going in that same pattern, but we'll stop there. I'll show you how we're going to show that. Now, in the negative direction, I'm going to do the same thing. So negative pi over 4, that's negative 0.7, negative 1, negative 0.7, back to 0, positive 0.7, positive 1, 0.7, and then back to 0. And what we get is this nice pattern. So again, we could have picked any other angle, so we're going to go ahead and connect this with a smooth, continuous curve to show that the graph keeps going. We're going to go ahead and just extend and put arrows on the end, because just like a normal graph, if we're showing that it continues, the arrows will show that it's doing that. So we have our values. All right, so that's a graph for sine of x. So we're graphing between negative 2 pi and positive 2 pi. But again, this graph cycles over and over again. All right, so what's our domain, our input? And again, I'm going to write the word angle here. These are angle measurements. You can use whatever you want because we could pick positive angles, negatives, whatever we want. So it's all real numbers. I'm going to go ahead and write that in interval notation. And we can also write it in our lovely, cute little r. The range or the output, like what kind of ratios we get, though, we do have to talk about, because this graph doesn't continue to increase or decrease like up and down, because think about SOHCAHTOA. When we think about our SOHCAHTOA ratio, sine is the opposite over the hypotenuse. You're never going to get a ratio that's bigger than 1, right? Because that would mean your opposite side is longer than your hypotenuse, which cannot happen. So when we look at our graph, it looks like the smallest number, remember what we do range, is looking from where there's the smallest value for y up to where is the biggest value for y. And it looks like we're going from -1 up to +1. So our range, and including those ordered pairs. So when we write our interval, it would be -1, 1. So that would be our output. We're only going to get ratios between those two values. Okay, let's talk about period. I'm going to actually have you kind of label on your graph. If you have a highlighter, this might be helpful, because then you can actually see what this is going to look like moving forward. So I'm going to go ahead and highlight one complete period. I'm going to start at 0. So it goes to a max, to the middle, down to the min, and then back to the middle, and it would start repeating itself right there, right? So that's how long one complete cycle is. So the period of the function is this distance right here. So I'm going to go ahead and actually label it on my graph. So that's the period. How long did that take? Well, it went from 0 up to 2 pi. So the length of one complete period is 2 pi radians. And notice back here, here's another one, right? That's 2 pi long. That's the same distance. So this is another period, another cycle of that function. All right, let's talk amplitude for a second. Remember how we calculate amplitude? It's 1/2 the max minus the min. So we can think of it as like an actual formula, but you can also just look at, okay, where's the maximum, where's the minimum, and take half of that. So from top to bottom, if we're going from -1 up to 1, that's 2 units long. Half of 2 is going to be 1. In other words, that's the amplitude and that's the amplitude. So let's go ahead and fill that in. So we've got 1 minus a -1, half of it. Just be careful when you subtract a negative. That's half of 2, which is 1. Most people never actually do the formula. They would just say, look at the picture and be able to answer it. So I'm going to go ahead and write that in there too. This is the amplitude right here. So that's 1, and the amplitude over here also 1. So I like to think of it's the distance from the middle to the top or the middle to the bottom. So it's like the height of the whole wave cut in half. So that's what our graph looks like for sine. So sine of x, pretty straightforward. It cycles. Lots of things like sound and light that have waves that look like that. All right, let's take a look at cosine. We're going to do the exact same thing, and we're going to go ahead and graph cosine. We're going to use our unit circle again, so we're going to pull that out. Remember, for cosine now, cosine is the x values. So you're going to be looking at the x values now, oopsies, for all of your ordered pairs that they're asking you for. And again, I just picked some of the values. We certainly could do more if we wanted, but this will give us more than enough values to be able to make a good picture. So go ahead and take a second and fill in from your chart your cosine values. And remember, every square root of 2 over 2, we're putting that in as a 0.7. So go ahead and pause and fill those on in. So we have a positive 0.7. We get to our minimum at 0, or middle at 0 for pi over 2. 3 pi over 4 is negative 0.7. At pi, we've got our -1. 5 pi over 4, we're down at negative 0.7 in quadrant 3. 3 pi over 2, we're at 0. And 7 pi over 4, we're at positive 0.7. And then back to 1 again before we start cycling. Now remember what we did for the negative angles. We're starting just in the same location but going counter or clockwise, pardon me, so the opposite direction. So negative pi over 4 would be our quadrant 4, so 0.7. Negative pi over 2 would be a 0. Negative 3 pi over 4, that puts us into our quadrant 3, so negative 0.7. Negative pi, halfway around the circle, that gives us our -1. Negative 5 pi over 4 puts us into quadrant 2. And then negative 3 pi over 2, that gives us back to our 0. Negative 7 pi over 4, almost all the way around. We're back to quadrant 1. And then we have our all the way around the circle. We get back to our 1. Now, what's interesting is if you take a look at those values, they're really the same as the ones we had for sine, right? Just in a little bit different cycle. Where we're starting in the pattern is just a little bit different because we're using the x instead of the y. So it just has to do with that opposite versus adjacent. So we're going to go ahead and do the same thing we did for the last one. I'm going to go ahead and label 2 for each here, and we're just going to plot our points. So for this one, at 0, cosine is actually at its maximum, where if you look back at the graph for sine, sine at 0 was 0. It starts in the middle. Cosine starts at a max. So we start at our maximum, and we got a 0.7, then a 0, negative 0.7, then we're down at our minimum at pi, -1. And then negative 0.7, back to 0, 0.7, and then we're up at 1. And again, this pattern would continue infinitely in both directions. We can continue that on. My table stopped at 2 pi, but the graph doesn't. It definitely keeps going. In the negative direction, we got our 0.7, our 0, negative 0.7, -1, negative 0.7, 0, 0.7, and then a 1. And again, connect that with a nice, smooth, continuous curve, because we could have picked any other angles that we wanted. We could have done the other ones on the unit circle. We could have used our calculator. Now, it should continue going down. We're at our maximum. So when we finish this graph off, make sure your arrow goes down. Same thing at the other end, because the next point would be a 0.7 again, right? So we got to be careful. It never goes above 1 or -1, because again, SOHCAHTOA, now we're doing cosine, but same argument. Cosine is adjacent over hypotenuse. That ratio is not going to be bigger than 1 or less than -1. Remember, negative just means direction. So we got to be careful how we draw that graph. All right, so let's talk about what we know. Domain again, could pick anything I want, so all real numbers. And our output, our range, again, distance between the top and the bottom here. So the bottom number looks like -1 to 1 again. All right, what is the period? Remember, that's the length of one complete cycle. So I'm going to go ahead and highlight again here, and I would encourage you to do that as well. I'm going to go ahead and start at 0. It starts at a max. goes to the middle, down to the min, through the middle, and back to the max. That's one complete cycle for cosine. So when I think about what those values are doing, I'm going to go ahead and draw that on here. This right here then would be the period of that function. So how long is that? Well, it started at 0 and it ended at 2 pi. So it has the same period as what sine did. And here's another one. So that's a second period for that function. Kind of nice to have that drawn in on your graph so you can have that picture in your head. All right, how about amplitude? Remember, that's half the max value of the function minus the min, or the height of the wave divided by 2. Well, the height of the wave is 2, right? So if we do our maximum of 1 minus the min, so half of 2 again, which would be 1. Now, once again, you can just probably look at the picture and be able to tell. So the amplitude is the distance between the middle to the top or the middle to the bottom. So amplitude is a measurement of how tall the wave is, middle to the top or the bottom. So sine and cosine are super similar. I'm going to lay them over the top of each other here so you have this picture. So cosine and sine, which one's which? Let's see if we can label these. So which one started at the maximum value? So that was the one that we just did, right? So that's the cosine graph. So I'm going to go ahead and put the labels over here if you could label them as well. Cosine is the red one, sine is the blue one. So are they basically the same graph? Well, they go up to the same maximum values, the same minimum values. They cycle the same distance. They're just shifted off, right, a little bit from each other. And they're shifted off one interval, one tick mark. And remember, if we're thinking about what our scale is, if this is pi, this interval would be pi over 2. So they're 90 degrees off, sine and cosine, those co-functions. That's because those opposite and adjacent just flip-flop. When we think about our SOHCAHTOA triangles, so the graphs are just going to be off by 90 degrees as well, as with those opposite and adjacents are interchanging. So they're basically the same graph. They cycle through the same set of values around the unit circle. And there's a whole bunch of things that we can do with this. There's lots of different equation solving we're going to get to, but these are the parent graphs, right, that we're going to be dealing with. So just a couple quick sort of follow-up questions on the graph, and then we should be good to go. All right, so it says for which values of theta, so remember theta is your angle, for which cosine is equal to 1. So we're looking for when the cosine value, the red graph, is 1. So we'll see if you can find on the graph any places where that happens. Well, cosine is 1 right there, so that would happen at 0 radians. But gosh, it happens again here. It's 1 also. That's at 2 pi. So I'm just going to kind of make a list here. But it happens here also, which is negative 2 pi. And there's going to be a whole bunch more. Can you predict when the next one would be? Well, if the length of the period is 2 pi long, if it happened at 2 pi, what would 2 pi later be? Well, 2 plus 2, that would probably be 4 pi as well, and then 6 pi, and then 8 pi. If you know it's periodic, that's the cool thing about these functions, is we know when these things are going to happen again. So let's try one more of those. When is sine equal to 0.5 or a half? Okay, we might need our unit circle for this so we can figure out what those values are. But let's take a peek. When is sine going to be a half? So I'm going to go back to my unit circle here. So for what angles is sine a half? So we're looking at our y value. See if you can find any on here. I see one there. So at pi over 6, I see one here. That's at 150. When is it going to happen again? Well, when I get all the way around the circle again and get to something that's coterminal or ends in the same spot. So what's cool about these is there's actually infinitely many places where these are going to have the same values because they cycle. So 30 and 150. If we're just looking in the original, or if you want it in radians, pi over 6 and 5 pi over 6. So we have lots of different options, and then etc., right? It's going to continue for all the places where it cycles back to that same value. So we're just starting the process to make sure we understand what these functions look like and then be able to work with them. So ultimately down the road, we're going to be putting in some writing equations of these things, looking at all the different transformations that you've done for every other parent graph. How do you make a graph go up and down? How do you make it go left and right? Where do you put those numbers? How do you stretch it, compress it? Think of all the things you did with every other parent graph. That's what's coming up next. So for today, though, we just want to make sure we are okay understanding the difference between the graph for sine and the graph for cosine and being able to identify a periodic function.